Failure of materials and fracture and the defects, right? So mainly uh, failure and fracture, so both are something very equal in meaning. And again, defects, so defect means if defects occur, then it will go for failure or fracture. That is the relationship in between failure, fracture and defects. Mainly the failure of materials can take place due to many reasons, like plastic deformation maybe happen, because after the plastic deformation we can see the fracture. It may happen due to creep, fatigue, degradation, or something like some kind of disasters, sudden dislocation movement. Likewise, there are some reasons. So up to now, we have identified what is materials and what are the properties. Then we need to understand about the fracture or failure. So ultimate results is the fracture. So after this happens, that means there are so many failure reasons. I think you may heard about this. Some disastrous conditions, like failure of bridges, failure of buildings, failure of machines, right? So early days you may heard some new as well. So the type of fracture is mainly depends on the material, stress structure, atmospheric nature and temperature. That means the conditions, right? So it's very important that when we are designing something, right? So most of the times we design up to the yield limit, but it is something that expected to go for more than yield, because fracture is there, right? So there are some kind of notifications before the fracture in some materials, but some of them may not. So we have to deal with that when we are doing the design. So for making them safe, we are adding called safety factor, right? We have some margin. So as example, if some kind of material fails in 100 newtons, we try to improve that limit into 150 by adding material properties. As like when you are designing a building, or when you are designing machine element like gear wheel, shaft, key, right? So we ready to make some kind of adjustment for safe, right? So that is what we call safety first. So after failure we can't do something like safe, right? So before that we have to design up to safe limit. So that is what we call safety factor. The fracture that shows a large amount of plastic deformation, generally referred to as ductile fracture, while that which occurs after little or no plastic deformation is called brittle fracture. Because here you can see these are the two different ways of fracturing, right? We call types of fractures. So this is what we call ductile fracture. This is the brittle fracture. You can see the difference. In the ductile fracture, after some time, we can see some deduction of cross section in some area, right? We call that necking. Necking means you can see there is a shape like neck, right? So it shows that it going to be fail in near situation, right? That is what it shows. But in brittle fracture, we cannot see any kind of shape reduction or any sign of saying I am going nearly in the fracture or failure. It did not happen in brittle fracture, like ceramics, like concretes, right? So also concrete is also one of a brittle material. It doesn't show any kind of sign before failure. So those two you have to identify, because when you are doing designing with brittle materials, you have some kind of safety limit to work. But in brittle, it doesn't occur like that, so you have to apply a higher safety factor for this. So that is why ductile showing the well-known cup and cone structure, brittle, crystalline appearance, that means you have a sharp edge. Right here you have a sharp edge, that means flat like surface. So both are going to be failed in some time, but sudden failure is occur in brittle failures. Right, so you have to identify that when you are doing design. The brittle fracture occurs as a result of complete and sudden separation of atoms, layers as indicated in previous figure. The reason for the separation can be explained by using the theory of energy conversion. So assume the bonds holding the atoms together are made from elastic material, and that the applied force, that means this force is maybe created through external stresses or internal stresses like residual stress inducing during manufacturing processes. Manufacturing means I also mentioned that some heat treatment processes and again machining processes. So within those processes, there may be some internal stresses and against external stresses that already I have mentioned in previous case. So these result in strain energy being stored within the material. So if the applied force is increased sufficiently, the bond will snap with release of strain energy. So after the strain energy, it will go in some kind of failures or fractures. So this energy is used to make new surfaces of the crack, where the formation of surfaces requires energy. So I already showed you how the dislocation is moved to the edge or into the boundary. So after the boundary, there are no any kind of ways to making some bonding. So without bonding, that means it tends to propagate the crack. So after propagation, it will suddenly break. So this is the main reason why the real strength of the material is substantially lower than the theoretical strength of the material as derived from the interatomic forces of the bonds. So I already showed you how that bonds is moving. When you apply a force, when you are making a shear force, how these bonds are moving with one to another. So this type of cracks are observed in non-metallic materials like glass, ceramics, concrete, and thermosetting plastic. Right, those are you can see the brittle fractures and means sudden failures. In metals, right, you know, when you have a wire, metallic wire, you have to rotate it like some periodic times to break it as a wire. But if you have a material like glass, you do not want to do it like periodic times. It suddenly breaks, right? That is the nature. So in metal, brittle fracture, plain or brittle fracture occurs mainly in BCC and HCP crystals. Are present and rarely in FCC crystals. Some may form this brittle fracture or brittle failure, right? Because due to some conditional change like temperature. I think you know that when those cast irons, right, we call cast iron, those are alloys, right? Cast iron like your engine body, right, or your cooking equipments also made out of some cast irons, right? Some of them, if it going to fall into some ground, right, so if it fall into ground, that will break some kind of equipments, right? Those are made out of cast iron, right? So that is something what we seen like a brittle fracture, because the amount of carbon if increase, it goes to brittle, ductile to brittle. That is why it shows the brittle fracture. Here you can see that cleavage along crystallographic plane of brittle fracture. That is how you have applied to stress, right, sigma stresses. then how this crack propagate into the material from the edge, right? So when you are dealing with these fractures, right, so some of the scientists observed what is happening and they try to give some predictions like things, right? So it forms their theories. So Griffith is one that he do some kind of observations about cracking or fracture, right? So he makes some theories, what is called Griffith's crack theory. So he shows some identical points to study before making that material to the fracture, right? So he studies something and gives some theories. According to his theory, the propagation of a crack, because if there is initiation of a crack inside a material, it's not a kind of an issue, because if it propagates, then it tends to break. So without propagation, only the initiation is not enough to go into the fracture, right? So that is what we call propagation. Of the crack is depends on the critical length of an existing crack, we call micro cracks, under given mechanical stress. So this can be explained by an energy balance considered as in previous paragraph. Any real material contains micro cracks and those will be the places of nucleation for micro cracks, and that will, so that is theory explain the condition for the propagation of the crack in brittle materials, right? So by considering a lens shaped micro crack of length 2c shown in last figure in piece of material with a unit thickness and crack runs from the front to the back face, right? So after propagation that crack will run, right? So if the longitudinal tensile stress of sigma is applied, the crack tends to increase its length in transverse direction. So with increase of the length, the surface area of the crack is increased. So while the elastic strain energy stored in the material decrease, so this is because the elastic strain cannot be continuous across the crack region. Here, there are some of the stresses, like, so those stresses can form this kind of bonds movement. So here you can see that bonds is missing. So due to missing of this bond, it makes as dislocation. So if this dislocation comes into the edge, I already showed you how this goes as separation. So if the separation occurs, then the stress can uh, propagate that dislocation, right? That is what this one says. So if the surface energy per unit area of a material is Y, then the surface energy of a crack is 4 gamma C, right? Due to two surfaces, right? 2C into 2. Here 2C is the length. It's into 2, that is 4C. Then multiply by gamma, then 4 gamma C. The elastic density of the material is half sigma E is the elastic module, right? Because this is a work, right? I mentioned how to get the toughness energy that under the graph. Likewise, uh, it shows the elastic density half sigma E, right? So this is the energy U as a function of the crack, how it tends to go, right? Half, this is the half width and this is how it increase. So here you can see both 2C and 2C, right? So the Griffith equation is also valid for surface crack with a depth of C, and they have the same defect as an internal crack with the length of 2C. So therefore in a particular material, surface cracks are more effective than internal cracks. Right here it mentioned how it the crack propagate in the surface, on the surface and in the material. So in some materials, a crack may not propagate even after the Griffith condition is satisfied due to the lack of stress concentration at the crack tip. The propagation of a crack is the separation of atomic layers by breaking interatomic bonds at the crack tip. For this particular action, stress concentration is required, which should be equal to the theoretical stress required to pull apart atomic bonds. Right here, what I mentioned uh, is that if the stress concentration, that means uh, stress need a path to transfer. If not, you know that if you apply a force, if there is no connection into another atom, like you have a connection within that atomic lanes, like, or that means you have a connection within the atoms. If you apply force, then it will transfer to another atom, then another atom, like it goes. But if you do not have any connection within those atoms, that stress cannot transfer, right? So if there is lack of connection with atoms, then there is no any transfer of stress. But that's not here. That means we have transformation from atoms from surface to interior. That means inside, right? So the stress concentration, that means if you have like stress concentrations, like that means transfer of stress, right? That sigma mass at the tip of the crack, when an external stress sigma is applied, then sigma max to crack equals 2 sigma root c over rho. Rho is the radius of curvature of the tip of the crack. That means here you can see there is a small tendency of applying of stress, right? So after applying the stress over any crack, you can see there are that parallel lines are get together in regions like this. This is called stress concentration, because stress can move from here to here if you have a straight lines. But if you have a crack, then that stress is transferred like this kind of curvature, right? Because there is a lack of connection inside the crack. So I already mentioned, if you want to transfer the stress, there may be a connection in between the material or the atoms. But here you have a void or crack. And crack means there is a space, right? There is a space within the atoms. So then that atoms cannot make a connection. So they try to escape from the crack or void, then move it to another side and come back like this. So that is called stress concentration due to void or crack. Here also you can see these parallel lines go along with this one and turn it. So the turn is happen some kind of increasing of the parallel lines. So that increasing of parallel lines in some areas called stress concentration is increased, right? So that is what mentioned here. So maximum sigma or the stress that need to get a fracture, right, is that you can apply this equation. Sigma mass equal to sigma root c over rho. C is the crack length and rho is the radius of curvature. That means radius of curvature means this one, right? So here you have a curvature, here you have a curvature. That is what they mention about the radius of curvature at the tip of the crack. So in ductile materials, during plastic deformation, the radius of curvature at the tip of the crack will increase and the stress concentration will be less, and therefore the propagation retards, right? So if you have a huge crack inside the material, then it doesn't try to transfer the stress from one side to another. It will try to increase the crack with the internal stressors. Ductile fracture, the fracture failure in metals is more predictable than that of brittle metals, and therefore they are more stable for fail-safe engineering design, right? Because they showed something before fracturing or before cracking. So under mechanical stress, as plastic deformation begins, the tip radius of the microcrack present is likely to increase, and this will automatically reduce the stress concentration because due to transformation. So which retard the propagation of the crack. It is fairly difficult to distinguish ductile and brittle fracture surface with naked eye, since some brittle metals undergo some ductile deformation before fracture. Under optical and electric microscope, it can be seen that a mass of minute facets which reflect light strongly and reveal the crystalline nature of the metal. Or on the other hand, completely ductile fracture shows a rough, dirty gray surface because much of that surface has been deformed along the general plane of the fracture. Here it shows how we can identify a brittle fracture and a ductile fracture, right? But in some cases, they mention you can't see them within your naked eye. You have to use a microscope, we call electron microscope. So within that also, so they put some light onto the crack or into the material and show and inspire that how the material transform the light through the atomic spaces. So even though they have identified the reflection after going through the material, they give that the fracture may be ductile or brittle. Right? That is how they identify. And again, you have ductile brittle transition. As I mentioned, there are some disasters like Titanic failure, right? Ductile to brittle transition. Because when you are dealing with steels or metals, so if you try to increase the temperature up to high degrees, then they try to melt. So that melting means you transfer your phases. That phase transformation is what we have a transition material. The working temperature of component is also a very important factor for the behavior of metals. So as the temperature decreases, the movement of dislocation become more sluggish, so that the internal stress may exceed the stress needed for propagation of cracks. Right? You can see internals may exceed, right, to propagate the crack. Therefore, the brittle fracture is more likely at the low temperatures and may even occur at ductile materials if the temperature is sufficiently low. So that means if you try to reduce the temperature of a metal, right, so you can have some kind of experience. If you can put a metallic bottle inside the deep freezer and took some amount of time and see, you just take it immediately and drop it into a flow, right? So you can see a kind of a crack, right? Suddenly crack. That is due to reduction of the temperature, and it happened due to the ductile brittle transition, right? So that ductile material, it transit into a brittle material due to the change of temperature, right? So this observation is very important in design process when selecting materials for the components operating at sub-zero temperatures versus Arctic and space vehicles, like what I mentioned in Titanic failure, right? So they didn't identify this glass transition or what we call ductile brittle transition temperatures, right? Because after their failure analysis, they quickly mention this transition temperatures because it goes to lower temperatures, it freeze, right? That solid freeze, and they tend to make it like ceramics, right? So these metals is behaves as ceramics in low temperatures. That is what their conclusion. So the metals with BCC and HCP crystals. So please mention this one. The metals with BCC and HCP crystals such as steels, ferritectic, beryllium, chromium, molybdenum, tungsten, zinc suffer from low temperature brittleness. So that is very important. So when we are going to design some machine components to use in low temperatures, like this type of uh, offshore activities in like Arctic, Antarctic, right? Those type of areas or near glaciers. So those are like low temperature activities. So if you use these steels, beryllium, chromium, molybdenum, tungsten, and zinc like uh, metals for your applications, if you try to use tungsten rods or zinc coatings, right? Steel nuts and bolts like things, so they will tend to break in low temperatures, right? So if you try to use these things in your machines with low temperature activities, then suddenly if you apply a force, if you apply some kind of stresses from externally or internally, then definitely it will break, right? That is the most important part of knowing this type of behavior. So in figure shows the relationship between brittle fracture and temperature of different metals, and the temperature at which fracture shows 50% brittle and 50% ductile, called ductile brittle transient temperature, DBTT. The presence of carbon, phosphorus and nitrogen raises the DBTT for mild steel, and those impurities should be kept at a minimum when the steel is used at low temperatures, right? Like a Titanic disaster. Yes. Right. That figure shows the relationship between brittle fracture and temperature of different metals. Right. What we discuss. It means the presence of carbon, phosphorus, and nitrogen raises DBTT for mild steel, and those impurities should be kept at a minimum when the steel is used at low temperatures, like Titanic disaster. The lowering elements like nickel and manganese depress the DBTT, and steel plate used for the welded hulls of ships operated in a cold North Titanic will contain only 0.14% carbon and 1.3 manganese. So that is the kind of actual thing happen, right? So due to uh, the limited uh, allowing elements, right, from uh, designing purpose. But now you can see after this type of transition temperatures, there may be formation of cracks, and they try to propagate due to condition changes like temperature. So if the temperature gets low due to the internal and external stresses, it tends to propagate. So if the crack propagate, then there may be a sudden failure. Right here, the relationship between brittle fracture and energy has temperature of austenitic and ferritic steels. So if I mention these names, you need to go to phase diagrams and imagine what is happening on austenitic and ferritic, right? You know that tick, toy like those, now you have familiar with that. So we'll see at the low temperature here, right? This is the brittle fracture, but at the higher temperature you can see the impact value. That means the absorption of energy for fracture, it is high. So that means it can absorb more energy before fracture. But at low temperatures, right, the absorption of energy, that means impact value, right, so for fracture is low. So that means if you increase energy as like with the application with your design, right? As example, uh, try to imagine that if you try to make a propeller for a ship, right? That apply like 100 newtons, right? As external energy. external force. Then this limit is 100, right, with the temperature like 30, 40. But that propeller comes to a stage inside the sea like minus 60 degrees, like, right? Then what happens? To fracture that propeller needs like 40 something, 40, 50 like something to fracture. So you design that one up to 100. So if you apply a force like 100, so like 60 degrees Celsius, minus 60 degrees Celsius, it will definitely break, right? So that is how this transition temperature is important. So here you can see the ductile fracture, austenitic FCC states. So it tends to become ferritectic BCC, right? 80% brittle with ductile fracture at reef. Then it transfers totally into brittle fracture due to the FCC transformation with the low temperatures, right? So that is the importance of knowing these transition temperatures and with the alloying elements, right? How we transfer from different temperatures. Here also the variation of impact functions of temperature within different metals. Here you can see zero point 0.6 steel, then 0.45 steel, then nickel. There is a pure iron. You can see how it changes suddenly. This is the impact energy. That means the energy that it can absorb before failure. Right here you can see the drastic failure here. Right, because like minus 100, it goes to near zero. That means it doesn't want any impact force to absorb. Suddenly it failed. Right, so that is how this kind of metals fail due to decrease of temperature. Here nickel is something different. You can see low temperatures it needs high energy, but high temperatures like 50, 60 needs low energy to break, right? That is the impact. Again steel have the changes within carbon percentage, right? So there is also you need to notify when you are dealing with some designing purposes. Again another failure, fatigue. So under the action of repeated or fluctuation loads, right? As I mentioned, if you want to break a wire, then you need to do some kind of periodic actions, right? So that periodically happen, it generates some amount of stresses internally and tends to come into the dislocation into the surface. Then it propagates the crack, then it fails. So to need it to do that kind of cracking or the propagation, you need some time, right? So that time means the plastic deformation. So that is why that fatigue occurs, that or fluctuation load metals become fatigue. Examples for that: the rotating shaft, connecting rods, aircraft wings, and leaf springs, which are subject to millions of cycle of alternating stresses during service. That you can see rotating shaft, right? While rotating, it will have some kind of periodic actions, right? Then connecting rods, as they have CV joint inside material, right? You try to rotate your steering wheel, and you have a rack and pinion there, right? It will have another kind of periodic action. Like those are what we call repeated or fluctuating loads, right? The fatigue failure can occur well below the yield strength of a material, and it's the most common cause of engineering failure. As an example, mild steel can fail at stress of 140 or the yield strength 220, right? So I already showed you the stress strain curve. The yield strength is the highest stress that it can absorb, but when you are using that kind of fatigue mechanism, it can break below 220, means like 140. So those are very important things that we need to understand while doing the designing. The fatigue life of materials can be improved by avoiding sharp corners, right? Polishing, then short peeling, carburizing nitriding surface. Another hand, it means we call decarburing, can reduce the fatigue strength. So they try to eliminate the friction between the surfaces or the layers, right? So due to the frictioning mechanism, they apply some kind of high temperature due to rubbing action, like so inside the material. So they try to avoid that. To avoid it, they apply using polishing effects, right? Short peelings, carburizing, or nitriding. Apply on these type of surfaces to reduce that, right? Because actually they can absorb some amount of heat, right? So absorbing heat can reduce the uh, exciting elements, right? You know, the exciting energy, right? So if it comes to the exciting stage, that electrons can remove, right? So they try to reduce that. So using that type of actions, they try to minimize the fatigue failure. Right here you can see represent a test piece suffering alternating stress of range is about a mean value of 0. Right here start from stress cycle 0. Uh, in a typical SN curve for steel, right, this one, uh, this is the cyclic load. Then the 3 is a SN curve for typical of many non-ferrous alloys and some steel, particularly those operating under conditions promoting corrosion. Likewise, this is how the typical one goes like in fatigue failure. Some kind of practical one is here. This is the application. Here you can rotate, right? So this is the cantilever test piece. Then if you rotate this one, it goes to downside, and if you rotate again, it comes to up, right? This is the cyclic action. So if you, as I mentioned, when you need to break a wire or something rod, then you need to do it in some kind of cyclic actions or periodic actions, right? You have that practical experience. So if you do it, so that is how the uh, fatigue occurs and how the material tends to fail, right? So if you start with high cyclic loads, right, this is a high stress, then this is a number of cycle need to fracture. So if you have high stress, then low number of cycles. If you have low stress, high number of cycles. That is how it trends. But here you can see with the practical situations, due to some amount of kind of impurities and that purity issues, like it will change like this, right? So there is a fracture, and that is what happened after the fracture, and there are some kind of failures like brittle, ductile, and fatigue. So those are happening due to our material structural changes. And again, if you have another what is called defects, right? So that crack will happen due to the defects also, right? In the previous case, we mentioned the stressors, internal and external. But that stressors also can induce, that means initiate, if you have like defects in your material, right? Okay, we'll discuss something about the defects, right? So we have to identify what are the defects in crystals or solids, because you don't have any defects in your liquids or gases. Only thing you can see defect will form in your solids. So here also you can see this is a defect because that atom is missing. Again this one is missing, blue one missing, red one missing. But something here you can see that red one is out of this order. The missing element comes into here. That is also a defect. This is called Stokes defect, and this is Frankel defects. And there are some kind of we'll discuss here crystal defects and the imperfections. Right, perfect you know, right? What is called perfect, but imperfect is something different. So an ideal crystal is a perfect crystal in which each atom has identical surrounding. Right, we call that is ideal crystal. That means the bonding in between two atoms, they also equal. If you get it from north side or west side, then again up and down, top to bottom, if you select any bond, those are identical to each other. Right, it is called ideal crystal. But in real crystals are not perfect because those bonds are not equal. I already uh, showed you what are the type of bonds, right? A real crystal always has a large number of imperfections in the lattice. Right? Since real crystals are finite size, they have a surface to their boundary. Right? So inside surface you have a boundary. So at the boundary, atomic bonds terminate, and hence the surface itself has an imperfection. That is the word. At the boundary, atomic bonds terminate because after the surface, after your outer surface, there is no any connection from surface to another. If you have a connection, that is not the surface. So that termination from the surface is called the imperfection. So one can reduce the crystal defect considerably, but can never eliminate them entirely. Right? But you can reduce the crystal defect, but you can't eliminate. That means if you have a surface, then definitely you have a kind of imperfection. Uh, the study of imperfection has a twofold purpose, right? They actually study about the imperfections, what will happen, because imperfections also one of a cause that influence for the cracking, right? A better understanding of crystals and how they affect the properties of metal. That is one purpose. Second, exploration of possibility of minimizing and eliminating these defects. That is the actually important one is that you have to minimize or eliminate. The term defect or imperfection is generally used to describe any deviation from the perfect period array of atoms in the crystal. So you can see this is different from what we discussed in the previous failures or fractures, right? If this crystal happens, then we call that is imperfection. So that also initiate or try to nucleate the crack or the fracture. Crystal imperfection can be classified on the basis of their geometry. Right here, these are the categories we call types. First on point imperfections, what we here you can see, right? There's a point. This point is missing. And again, line imperfections. So that means line means this line will diminish. Then it will be a defect. Then again, surface means top surface. So another layer is then volume. So volume wise it means goes like cracks. Right. So we'll discuss what is called point imperfection. That means point defects. So there are imperfect point-like regions, 1 or 2 atomic diameter in size, hence referred to as zero-dimensional imperfections. Right. So there are different kind of point imperfection. It is called vacancies. So if an atom is missing from its normal site in the matrix, the defect is called vacancy defect. So it may be a single, di or tri. Here you can see this is missing. Then it is a point defect vacancy. In metals, vacancies are created by thermal excitation. Right? I also mentioned previous one. If it excite, we call excite atoms. Right? So then that due to the excitation, it will remove from the place. So when the temperature is sufficiently high, as the atoms vibrate around their regular position, some acquire enough energy to leave the site completely. So they absorb some amount of energy, then it get excited. So due to the excitation, they can go to another place. So when the regular atom leaves, a vacancy is created. A pair of one cation and one anion can be missed from ionic crystal. Such a pair of vacant site is called Schottky imperfection. So Schottky means you need to have pair of one cation and one anion, right? So it missed from the ionic crystal. So this type of defect is dominant in alkyl halides. So alkyl halides, you can see more Schottky imperfections right here, as like sodium chloride, right? Use easily they can move around. Here you can see this one also missing and this one missing. So both are missing. Anion and cation is missing. Then it is called Schottky imperfections. Then substitutional impurity. It refers to a foreign atom that substitutes for or replaces a parent atom in a crystal. So it will substitute or maybe replace. Then pentavalent or trivalent impure atoms doped in silicon or germanium also substitute impurities in the crystal. Here you can see the void is filled with another one we call substitutional. It will not affect to the properties, but it will change the properties, right? So at the present it will not affect, but due to some changes it will affect, right? You can see the size also. Then interstitial impurity, right? We call interstitial impurity. The interstitial defect arises when the atom occupies a definite position in the lattice that is not normally occupied in the perfect crystal. In crystals, packing density always is than 1. If small size atom occupies the void space in the parent crystal without disturbing the parent atoms from their regular site, it's called interstitial impurity. Here, your regular arrangement is there, right? But the impurity doesn't affect to the regular arrangement or regular crystal, but it gets some space here, right, without damaging to other arrangement, right? That is called interstitial impurity. In ionic crystals, an ion displaced from a regular site to an interstitial site is called Frankel imperfection, right? So due to ionic crystals, an ion displaced from a regular site to an interstitial site called Frankel one. So as cations are generally are smaller ones, so it is possible for them to get displaced into void space. So after finding some void, so they can displace. So anions do not get displaced as the void space is too small compared to the size of an anion. As you know, cations are small, anions are high, huge. That means their volume is high. So if anions replaced by cations, that is okay, but cations can't replace from anions due to the size. A Frankel imperfection does not change the overall electrical naturality of the crystal. So this type of defect occurs in silver halides and calcium fluoride, like silver halides and calcium fluorides. Here you can see this is the vacancy. This is a self-interstitial atom that is misplaced. Then this is a substitution impurity, and this is interstitial impurity. You can see this one is doesn't do any kind of harm to their original one, but it tends to come here. But this one is comes from another point, but same as that, it is also self-interstitial, but this one is vacancy and this is substitution. So it replaces from another part. Then again we call electronic defects, that errors in charge distribution in solids. We call electronic defects. These defects are produced when the composition of an ionic crystal does not correspond to the exact stoichiometric formula. Right? That means, so most of these ceramics or the other what we call advanced materials, like those are kind of uh, that their formula is not, we call exact stoichiometry. They have different type of stoichiometries. So these defects are free to move in the crystal under the influence of an electric field. It's due to external energy. It's like what you call electric field is external energy. So if they form that one, the presence of a point imperfection, right? So we call electronic due to the sufficient electric field or sufficient external energy. If we sufficiently supply that one to the material, that energy will have uh, initiate some excitation process inside those formulas, because their formulas are something called very high stoichiometric formulas, and they have huge number of atoms. So due to the excitation, some of them may change, like polymer chains, right? Because polymer chains, they do not have equal number of units, right? They have different type of units. So that kind of change happen inside due to the electric field. So that create one of a defect. It is called electronic defect. Then effect on point imperfections. You know what is point imperfection means? The presence of a point imperfection introduces distortion in the crystal. So in the case of impurity atom, because of it different in size, elastic strains are created in the region surrounding the impurity atom. Right? You know that when you are inside the class, if someone comes from outside into the class, or another your elder one or senior one, what will happen? Right? What is your kind of behaviors? What are your face changes? Right? So those are what we call nature that we experience. As like in the materials also, if they have experience with the impurity atom, they also tend to change their attitudes also. So that happens, and the regions and the surrounding atoms also uh, showing some kind of changes. So all these factors tend to increase the potential energy of crystal called enthalpy, right? So due to their changes, due to their uh, actions, due to their movements, these factors tend to increase their potential energy of the crystal. So we call that is enthalpy. The work done for the creation of such a point defect is called enthalpy of formation of the point imperfection. So if that impurity comes into that place, right, so it has to overcome some amount of barriers. So that is the enthalpy formation, right? Right. Next one is line imperfections. I think now you can clear what is point imperfections and what are the types, right? How the point imperfection happen, right? If it comes from externally or internally. Now we move into line, right? So only point is missing in the previous case. Now some uh, near points as a line is missing. The defects which takes place due to dislocation or distortion of atoms among a line in some direction are called as line defects. Right? We have now direction. In the point imperfections or defects, you do not have any line, only a point. But now here you have to identify what direction that line is performed. The line defects are also called dislocations. In the geometric sense, they may be called as one-dimensional defects, right? 1D, and it's only line, right? Not a kind of area, right? A dislocation may be defined as a disturbed region between two substrate perfect part of a crystal. Because if you want to define a line, you need 2 points. Without one, with only a point, you can't define a line, right? So if you have 2 points, then you can define a line. So in that case, you can see here more than 2 points is called a line. Then more than 2 point dislocation defects is also called line defect. So it is responsible for the phenomenon of slip by which most metal deform plastically. Right, in the line imperfection or line defect, you have two different types: edge dislocation and screw dislocation. Edge dislocation is in perfect crystal. Atoms are arranged in both vertical and horizontal planes parallel to the side faces, because you have 3D XYZ planes. Then they are arranged for those XYZ planes as parallelly. If one of these vertical planes does not extend to the full length but ends in between within the crystal, is called edge dislocation. Right? Okay, read it again. If one of these vertical planes, you know what is vertical means, does not extend to the full length, and there may be some kind of decrease of length, but ends in between within the crystal, is called edge dislocation. Right? So in the perfect crystal, just above the edge of the incomplete plane, that atoms are squeezed and are in a state of compression. So just below the edge of the incomplete plane, the atoms are pulled apart and are in a static tension. Here, this is what it says. Right, you can see only here, but it goes to something into a 2D, 1D direction. Right, here you can see it. It means it goes, right, it removed, then it tends to have a kind of dislocation. The distorted configuration extends all along the edge into the crystal. Thus, as the region of maximum distortion is centered around the edge of the incomplete plane, this distortion represents a line imperfection is called edge dislocation. Right? So represented by this one, or T or upper T, depending on whether the incomplete plane start from the top or from the bottom. So these two configurations are referred to as positive and negative edge dislocations respectively. Here you can see this comes here and stop here. So this starting and ending, then it is T1. So it's starting from here to here, then it is negative T. Like you can need it. Then there is a method that they started to nominate this type of dislocations, right? The points where you have the displacement. It's called Berger's vector, because you have direction here. Then to identify the direction, you need to have a vector quantity. The magnitude and the direction of the displacement are defined by vector called the Berger's vector. All right, the follow figure starting from point P, we go up 6 steps, then move to toward 5. Here you can see, right, because a vector you can identify the point what the imperfection is. Here you can goes to 1 2 3 4 5 6 and goes to downside 5. Here you can see the defect as like what we do in our vectors notifications. Then move towards like 5 steps, move down by 6 steps, and finally move towards left, reach the starting point, right? That is the starting point of the Berger's circuits. Then it is closed. So when the same operation is performed on the defect whistle, we end up with Q instead of the starting points. Those are the notations that we are used for our Burgers vector. So we have to move an extra step to return to P in order to close the Burger circuit. Right here, uh, goes starting from here, goes up, goes to this, and like this. You can actually complete your circle. There is no any misplacement. But if you go with this one, right, go along with P and comes here and goes after here you can see 1 2 3 4 5 6. Here also 1 2 3 4 5 6. You need to go down, so need to go down with this plane, not with per vertical plane. So then you goes 1 2 3 4 5 6, right? From that point you need to go with the horizontal one, right? 1 2 3 4 5 6 7, sorry, 7 1 2 3 4 5 6 7. 7 point you need to go horizontally. Again 1 2 3 4 5 6, you need to go 6 points. Then 1 2 3 4 5 6. Here you can see you are changing your starting point. So that means you are moving away from P, right? From end to starting you need to come to one point to the uh, one call your right side, then it is a vector point B. So we have to move extra step to return to P in order to close the Burger circuit. So the magnitude and the direction of the step define the Burgers vector BV, right? Then QP is B. The Burgers vector is perpendicular to the edge of the dislocation line. This is perpendicular to the dislocation. This is a dislocation plane removal. Then it is normal, right? That is what edge dislocation means. Yes, any questions? Please ask. Right. Then we move into screw dislocation. In this dislocation, the atoms are displaced in two separate planes, perpendicular to each other. It forms a spiral ramp along, that means around the dislocation. The Burgers vector is parallel to the screw dislocation line. Speed of movement of a screw dislocation is lesser compared to its edge dislocation. Normally the real dislocation in the crystals are the mixture of edge and screw. So in the edge you can see only a 2D one, but this one it is a 3D, right? Simply that Burger vector is something that complex here, right? Okay, we'll see. Here this is the starting from this point, right? So you can go along with this and go here. Likewise you can come to one of a ending point, but after starting you have a different allocation here, so then it should identify with the Burgers vector. Surface imperfection arise from a change in the stacking of atomic planes on or across a boundary. The change may be one of the orientation or of the stacking sequence of atomic planes, right? So there is a difference because the orientation, because here you need to understand this one through your 3D identification, 3D knowledge. Without 3D, that means XYZ. I think all of you have some kind of experience with a software like AutoCAD or SolidWorks, right? How to draw using a SolidWorks or AutoCAD with a 3D model, not with a 2D, right? Then if you try to adjust your XY plane and try to place a point in a point where we call 2 3 5, right? X is 2 and Y is 3, Z is 5, right? Z1 is 5. Then if you try to locate that point in your AutoCAD 3D plane, right? Then if you draw a sphere with the center 235, right? Then you can identify with rotating your axes about the kind of changes, right? If you change something, if you remove something from the sphere, then you can identify what is the plane or what is the point, right? Exact one, right? Due to the 3D move. Likewise, the surface imperfections arise from the change in the stacking of atomic planes or across a boundary. The change may be one of the orientation or of the stacking sequence of atomic planes. That means one or two. In geometric concept, surface imperfection are two-dimensional, right? So they are of two types of external and internal surface perfections are there, right? Then external one means, so they are the imperfection represented by a boundary. At the boundary, the atomic bonds are terminated. Likewise, I have mentioned like H1, but it goes to the surface, right? Then you have external surface, but in your edge dislocation, your surface is inside due to the void or due to that missing part. But here, this surface is goes to the external one. So they are the imperfection represented by the boundary. At the boundary, the atomic bonds are terminated. You can see it. The atoms on the surface cannot be compared with the atoms within the crystal due to the lack of bonding of the surface. The reason is that the surface atoms have neighbors on one side only, right? So in a, like here, you can see if you compare this one and this one, you will see. If you compare this one and this one, right? And again this one, these three, right? Here you can see this one has huge neighbor atoms. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, like 8 numbers here. But if you compare with this one, only 1 and 2. Right? Here you have 1, 2, 3, 4, like it comes. So that is the difference, right, with the external surface. So you have some kind of differences. So the atoms on the surface cannot be compared with atoms in the crystal. The reason is that the surface atoms have neighbors on one side only, whereas the atoms inside the crystal have neighbors on either sides. So they actually create those bonds with the neighbor atoms. So it has huge number of neighbors. Then this is shown in figure what I showed you. Since these surface atoms are not surrounded by others, these possess higher energy than that of internal atoms. For most metals, the energy of the surface atoms is of the order of 1 joule per square meter. That is the surface energy. Here you can see the changes inside the material and surface. And the surface also you have different areas, right? Here and here, these are also different areas. Then we come to internal surface imperfections. With the internal surface imperfections are the imperfections which occurred inside the crystal, right? So one I mentioned is the external one at the surface, but here internal surface inside the crystal. It is caused by defects such as grain boundaries or tilted boundaries or twin boundaries and stacking faults. Those are the types. Right, we will see what is called grain boundaries. So they are the imperfections which separate crystals or grains of different orientation in a polycrystalline solid during nucleation or crystallization. Right. So as what I mentioned in your crystallization stage, right? Crystallization and recrystallization. So they actually shows the difference of crystals and the grains, right? How the grains occur, how the crystals occur, right? I also mentioned what is the nucleation, then separation, right? Those are growth. All these are you have shown. Then they call the imperfection which separate crystals or grains of different orientation in a polycrystalline solid during nucleation or crystallization. It is a two-dimensional imperfection. During crystallization, new crystals form in different parts and they are randomly oriented with respect to one another. Right? Now you know what is grain boundary means and how the grains are arranged inside a metals or materials. Right? The different orientations because they have different shapes. Then they grow and impinge on each other. So due to the uh, lack of energy in the grain boundary, they are trying to impinge each other. The atoms held in between are attracted by crystals on either side and depending on the forces, the atoms occupy equilibrium state, right? Because they need to come to the equilibrium stage. Those atoms held in between the attracted areas in crystals, right? So each and every crystal is trying to attract to another crystals, right? Separate crystals. It may be 1, 2, 3, 4 like that. So due to that, the formation of different crystals, and they have separation area, we call boundary. So that is what you can notify as a grain boundary. These positions at the boundary region between two crystals are disordered. As a result, a region of transition exists in which the atomic packing is imperfect, right? Uh, so I'll do something like this. Okay, this is a one grain, and again this is another one, right? Again you have another like this one. So uh, if I show these areas, this one and this, right? These two, consider these two areas. So that boundary can use for this one and also this one, right? You do not have any margin at the end because you do not have a separation because this is a lack of energy level, lack of energy point. Then there is no any differences. So this grain, I'll note it as A. This one A, then B, and C. Right? So A and B can use this boundary here, right? And again B and C also use this one, but A and C can't use this one. Right? If you want something like if you have a D here, then D and C can use because due to the separation changes, right? That is the grain boundary here also. So these positions at the boundary regions between two crystals are disordered, right? As a result, a region of transition occurs, right? In which the atomic packing is imperfect. I think you know what is the packing factors of crystals for your cubic, right? The thickness of this region is 2 to 10 or more atomic diameters. Likewise, it change. The boundary region is called crystal boundary or a grain boundary. The boundary between two crystals which have different crystalline arrangement or different composition is called interface boundary or commonly an interface. Right? So I already wrote here the different areas, but they have common boundary, right? Different areas, common boundary, they have different kind of properties, but the area, that grain boundary, both of these grains can use. Like here, these are the arrangements. This is one crystal, this is again another crystal. So in between two crystals you have a area where you can't see exact arrangement, right? So that here you can see, you cannot see any. Here you have, here you have a good arrangement, but in this area you can't see any arrangement, like here also, right? Those are, here you can see, they actually name them as grains or crystals. So this one a crystal, this one again crystal, this one again, this one again, you have different uh, kind of boundaries. So from the boundaries they actually tend to break those arrangement of crystals, right? You have crystalline arrangement and again amorphous arrangement, but here we are discussing only about the slime one. Then tilt boundaries. So this is called low angle boundary, as the orientation difference between two neighboring crystals is less than 10 degree uh, 10 degrees. This disruption in the boundary is not so severe as in the high angle uh, boundary. In general, low angle boundaries can be described by suitable arrays of dislocation. Then actually a low angle teeth boundary is composed of H dislocation lying on above and the other. See the angle, so we'll see what is called. Theta is B over D, that is a tilt angle, where B is the Burgers vector and the D is the average vertical distance between dislocations. Here you can see, right? Theta is the tilt angle. Here you can see how these two changes like previous case, right? This dislocation starts, ends here, this one starts and ends here, and again this one start and ends here. There you can see the different dislocations. Now 1 2 3 4 5 6 7 8 9 10, right? From here to here, here 10, but now 1 2 3 4 5 6 7, now here to here you have only 7. 3 is missing due to this one and this one and this one, right? Those are the missing cases. So using that, here you can see the arrangement of this one is tilted, because it should goes from this and vertically this, but now it has some kind of differentiation. It is what I call theta. So if you find that theta, that is the tilting angle of this crystal. So that is how the tilt can be find here. This is the original distance D, right? Then B is one, that means we call Burger vector unit, right? Because Burger vector, you know, from x direction, you, this is the one unit, second unit, third unit, likewise you count. So that is called Burger vector unit. Then B is that. Then D is the average vertical distance between dislocations. So average one. So if you need to get the average, you can get the total and divide by 2. If not, normally you can see those two are equal, like, then you can collect something. So very that means perfect one is that you can get the total and divide into 2. Okay, we'll see. Then D here, B over theta. Then D number you can calculate here also, 1 2 3 4 5 6 7, right? So D is 7. Then B is your length divided by theta. Then theta you can find. So theta you can find B over D, right? Here B over D, also you can get the tilt, that is we call tilt angle. So if the atomic arrangement uh, on one side of the boundary is a mirror reflection of the arrangement of the other side, then it is called twin boundary. Uh, as they occur in pair, they are called twin boundaries. At one boundary, orientation of atomic arrangement changes. At another boundary, it is restored back. The region between the pair of boundaries is called twin region. So these boundaries are easily identified under the optical microscope also. Right here you can see both ends. This also changes, and again this orientation also change. Right, both, because if normal one is goes like this, right, so like this is a normal. But if one happens, right, it goes like this and goes only one. Normal one is this. But if second happen, then it should goes like this. Then both ways it changes. Then it is called twin boundaries, right? Twin action, right? You know the difference of action of two forces. When we call stacking faults, whenever the stacking of atoms or atomic plates is not in a proper sequence throughout the crystal, the fault caused is shown as stacking fault. For example, the stacking sequence in an ideal FCC crystal may be described ABCA, again ABC, 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 right? That is arrangement. But the stacking fault may change the sequence to ABC, then C is missing, right? Due to a fault. Then ABC, AB, not C, A, again ABC, right? The region in which the stacking fault occurs form a thin region and becomes HCP, hexagonal, and you can see that this thin region is a surface imperfection, is called a stacking fault, right? Here now ABC, 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 like, right? See this one, the arrangement is okay. But now starting from here, A is okay, B, C now, then A, B, C is missing, but some arrangements happen with the lines of these two, right? You can see how the lines changes and happen, and C1 is not there. Then now start with A, B, and again C is not there, but A, B, C now it comes, right? So those are the kind of faults you can identify. It is called stacking faults. So those stacking faults also happen to start something from the imperfections, right? So then it goes to uh, initiate a crack or initiate a dislocation movement inside the material and start to happen like edge dislocation. Then now we discuss about our imperfections like point imperfection, and comes to volume, then again surface, then now we come to point, line, surface, and now comes to volume. Volume imperfections. Volume defects such as cracks may arise in crystals when there is only small electrostatic dissimilarity between the stacking sequences of closed plaque planes in metals. Right? So presence of a large vacancy or void. So as example, as I mentioned in here, this one, right? So this is a volume, right? So inside the volume you can see a change. Here this one change and again this one change, because atrial something goes up from the original position, right? So three dimensionally you need to have kind of an imagination how it happens. So if it removes, so as example, as like a cake, right? This one is a cake. So if you try to get a slice from this, a parallel slice, then it is removed, right? So removed means you can see a volume there, right? You can see uh, some amount of x direction, in some amount of y direction, and some amount of z direction likewise. Then it is something we can identify as a volume wise missing, right? So volume defects such as cracks may arise in crystal, because crack also you can see only a 2D one, but it goes deeply into Z direction as well. Then some amount of volume is lost, right? So when there is only small electrostatic dissimilarity between the stacking sequence of close packed planes in metals, then it presents of a large vacancy or void space when cluster of atoms are missed is also considered as a volume imperfection. That means, if I say like this, if you have a we got a soil sample or soil cube, then if you just do a borehole from top surface and you remove some uh, soil from that surface and go into deep and remove some amount of soil from the inside as well. So removal from the soil sample, you can see there is a kind of formation that you can do with the removal of that volume sample. That is also you can form a volume, right? So that volume is misplaced, not a single atom or not a single line, right? You have a x direction removal, y direction removal, and again z direction removal. So the total will remove. So that removal is going to happen like the volume one. Then we call that is volume imperfection, right? Foreign particle inclusions and non-crystalline region which have the dimension of the order of zero point 0.2 nanometer, also called volume imperfections, right? So uh, the foreign particle inclusions and non-crystalline regions that have zero point 0.2 nanometer up to zero point 0.2, we also call that is volume imperfections. So if you have these type of imperfections, right? So there are so many imperfections that we already discussed. Then it goes to a point where we have like this. Already showed you this one. Here this one missing, both are missing. But here only one missing and it keeps a side like this, right? So all of these will happen due to some ways of finding energy for the excitation, right? Here you can, so this is the cracking, right? So inside this cracking you can see an amount of volume is misplaced, right? Because if you apply a stress here, this volume will uh, remove, but another volume will fill, as here. So this is your original position, right? These two are your original positions, right? So the starting is this. So sometime back, then this one comes to like this, then again this one comes to like this. So you remove this part, right? You remove this part, this one, and this one, right? You remove it, but separately you find something new, these two. So if you get it from volume wise, this volume is, these two are equal to the removal of this one. That is a physical actually appearance that also we can see, right? Only thing is it moves up or it's changed their location, but the challenge is that if it propagates through up to this point, right? So up to this point that is okay, right? Up to this one the separation is happened, but total one is not happen. That means uh, totally it is not separate into parts, right? But if this one separately comes from here to here, then we call that is a failure, right? Only this one is a fracture, but if comes to this point, then we call that is a failure. So that is the difference. The fracture can happen, right? Or dislocations, anything can happen, but it, if it comes to a point where there is a separation of their volumes or their regions with the material, right? So with the separation of these two regions, then that is a what we call failure, not a fracture, right? So fracture can happen if you have the excitation energy like this one, right, delta u, then it will propagate. So if the propagation comes to the other end from here to here, then it try to separate both two, we call permanent. If it separately comes to positions of two and means separate elements, then it is a fracture, propagation to a failure, right? So that is a failure mode of fracture. So now you can see the difference, what is called fracture, then what is called failure and defect, right? So those are the uh, imperfections and the defects. So after the imperfections or defects, then it will move to a fracture, is like this, but this fracture is not called failure, right? So these are the fractures happen, these are the imperfections happen, but that is not the failure. The failure means this has to come to here and to here, right? So this propagation need to happen to the 3D dimension. So if it comes to 3D dimension, then what happens? Those two get separate items. So if you have separate items like this, or this one or this one, if it separately comes to position where like this is what we call failure. So if the failure happens, then definitely that creates some kind of disaster for the material or for the application. So if that happens, then that ends up with some amount of uh, kind of accidents or something that we can't bear, like the Titanic fall like this. So we can't bear after happening this type of failures, right? So fractures can be eliminate something what we know now, but failures we can't actually bear. So that is the difference of fracture, failure and defects. So differences are there also with the brittle and ductile. So if you have ductile, you have something called safety limit, because it shows something before fracturing, before failure, not the fracturing. You have a fracture, but it shows something before fracture, failure, right? That is a brittle. But if you have it's a ductile. But if you have a brittle one, you have the fracture and failure equal, right? So that is the difference. So that is why we have brittle applications and again ductile applications. That's like concrete, because we can't just replace something to a concrete. That is why. So we can't replace a metal sheet to a concrete sheet. We can't replace a metal slab to a concrete slab. But we need to apply that. We need to use that brittle material. The thing is, you have to change your properties according to the application. That means, as example, if you have a 120 millimeter thickness slab in your roof, right? Definitely you can't replace that one by again another steel plate. A thickness is not as equal than 120 millimeter. It will reduce up to 50 millimeter or 60 with the metal. But the thing is that we can't do those connections as what we did in the concrete, right? Definitely you can't do. So that is why that application is there with the brittle material, right? If you have a ductile material there, right, those sudden failures in slabs like what you seen in the internet, right, sudden failures of buildings will not happen, right, will not happen. But the applications differentiation of brittle to ductile or brittle materials and ductile materials is like this. That is why you need to apply more safety factors to the brittle portion than ductile portion, right? You need to do that, you need to apply that to avoid this type of failures, right? So I think now we have come into our discussion ending with defects, fracture and the failure, right? So that's the difference in between these three words, right?